Okay, so last time we left off and we said one of our main things was just to sort of clean things up and get this in order. So I'm just going to do that here and show you guys a couple quick tricks about that. So last time we had said that if I look at this, right, those were our radii, the radius, the r value of the parallel axis theorem that we want to see in the one direction, right? So we had made this algorithm, right? So what I'm probably going to do here, I'm probably going to copy this so that I have this set up now, right? And have this guy go over here. And effectively what this allows me to do, you guys see how there's some buckets here and there's some buckets here, right? There's two layers of them. So if I just grab the inner layer, you don't need to do this, but I'm going to do this, and you hit the middle mouse wheel and you hit this button, it puts them inside a nice little package. And then what's inside here is the script that you had before. So a lot of times you'll look at my script and you'll be like, oh, it looks very, very simple. But it's because a lot of it's packaged. It's still simple. It's just the complexity of the script itself is hidden behind the scenes. I'm going to do that for the simplicity of getting this script a bit more clean, right? So RAIXX, right? Again, this also points to the fact that you should be working very cleanly because this allows your script to be very easily understood, right? We could just as easily kind of do something like this, where we do the exact same thing here. Okay, so now what goes in is a point and some geometry, and what comes out is IXX. So I could literally take the IXX now, copy it, and I could do something like this, cluster it again, and you see that. So it takes in the point and the geometry, and it spits out IXX. Again, all he's doing, I'm just going to write on here, sorry, parallel axis theorem. And there you go. There's something that takes in a point, a geometry, and it will tell you about that point what the geometries, in this case it's only two of them, what their moment of inertia is about the x-axis, global x-axis, right? So that's one of, we're going to keep it right now, just sort of, we'll just keep it like that, right? So we're going to say step 3, this is going back to our original scripts here, Rhino, go back, Facades. Our very original script, which was find Centroid, get the midpoint, and then get the mass properties. So we basically covered everything that we wanted to do, right? This is the last step in that. So this is step 4. And then you say calculate IXX. And we can get one for IYY later, but for now let's just keep it IXX, right, for simplicity's sake. Right, so that's the final bit there. Now, again, I show you this just to say this is the way it should look. You don't need to cluster it. I would highly recommend you consider clustering and being more clean about the way you do things. All right, so we discussed all that in the past few weeks, all these steps. Now, what we're going to do today is we're going to discuss how does this thing not really do for us what we need, right? So we got the output here. We have IXX of this piece of information. We said before if we do area moments that we get out the same number here as there. So it's 4.896, boom, same thing here, right?
That's the right answer, right?
Unless we want to do the integration ourselves, then yes, it's the right answer. So in general, this is what you would do anyways. You would actually just click this button and 4.8961, right? If you're not getting that from your script, it could be that potentially maybe I've jigged this one around, right? Obviously that changes it. You see how now it's live updating about the y-axis, right? So I'm going to undo all that. Okay, so big thing here today is let's keep it to IXX just for the sake of argument. Let's say we're only going to do major axis type of moments, right? We could obviously duplicate this, and I'm not going to go into that right now in terms of making it IYY. Let's do it one at a time. So what's the problem with this in terms of, this is a nice script. It's taken us 4 lessons to get to it. Some of us, I don't know, could do it on their own without any guidance now. Some of us maybe still would need to go and practice 4 more hours to be able to do this on our own. Commercially, for a business like ours, is this a viable script? Does this help us at all? Probably not yet, right? It's not much better. You say it took me 4 hours to do all this, and it took me 4 seconds to do this, right? So we haven't really been able to scale, right? So one of the things you might say is what happens, Emilio, if I turn on the gumball, if this happens, right? What if I've been given that? Is that the right moment of inertia? So if I go again and I say mass properties still matches my script, right? But it's about the centroid coordinate axes, right? So it's obviously, as we rotate it, IX is aligned to the world coordinate system, right? We had said that at the beginning. So we should watch it now as the number goes up as I do it this way, just from physics perspective, and it goes down as I go all the way to here. Okay, so we know that that's just a case of the physics of what we're playing with. We need to be able to take in, and we talked about this before, we had skipped over it. We had said originally that there's one step in here that is vital to what we need to do, which is rotate to the global coordinate system, right? So that's got to go in there. What's another thing that we still probably need to do? We probably will never always have the situation where it's 2 surfaces, right? So we need to make that a bit more generic as well, right? We want to be able to put in 50 surfaces, 100 surfaces, it doesn't matter. I just want to throw in geometry that represents the cross-section.
Could be 1, could be 3.
Yeah, you guys have very complicated things sometimes, right? So it has to be a generic thing. And then also, it might not be something that's a surface. It might be something that's the edges of the surface, right? And then we talked about how, if I just show you guys, so you guys might have actually this. Right? Some CADsman or somebody might have sketched that out for you. So you might be trying to sit here and go, please create a surface out of that. But, you know, down on the microscopic level, there's 2 lines overlapped and it won't join, right? So all of those things, we still, 4 hours in, we're still probably another 4 hours away from where we need to be to have this be commercially viable in any way, shape, or form, okay? So it's all the more important to keep doing this, but also keep practicing, right? Because you will start to forget hour 1 today, right? And by the end of this, you'll have completely forgotten it. So let's start by addressing the elephant in the room. We are going to be given what we want to end up doing eventually. If I just undo what I just did over here. What would be nice is you might be given, I imagine in real life, you'll be given that, right? And you'll want to do each one of them. Let's say at first, just grab this one, press a button, give me a thing. Grab this one, press a button, give me a thing, right? Eventually, we want to grab all of them and have it just do it all for us. But we'll just do one at a time. So the key thing here is now, we have to go back and we have to say, okay, we already recognize this. We need, early in the script, to rotate this geometry to the global coordinate system. So where do you think we start with this problem? It's a rigged question, by the way. We start on paper, right? Rigged question. So, again, habit has to be, if I want to solve this problem, I come onto this canvas here, onto your piece of paper. Everybody should try right now to think about what they would do. If your input is, I'm just going to draw it like this, and you have global coordinate system. Oh, I'm going to do it again, like last week. There we go. Input is this, and output is we'll call it E1, E2, and then we'll call this one to E1, where E1 is parallel to X. All right, and X is perpendicular to Y, therefore it's all good, right? That's effectively what we know we need, right? And we need it because the tool that we have at our disposal to get us that integration, recalling that our last step was the integration, this guy, he inherits, we don't think of it normally, but he inherits the global coordinate system. So we need to massage whatever we do into the global coordinate system. So what can we do? First of all, I'll ask the question, do we have E1 and E2? Should that be in the inputs of this? Do we have E1 and E2? What do you have? What have you been given in this problem statement? Both from an English perspective and a data perspective. What did I give you? Eugene, what did I give you? What did I literally physically send you in an email? Or send you a Rhino file, right?
Yeah.
And what's inside that Rhino file that we've been playing with?
Profile.
The profile of a mullion or something, right? Yeah. Data-wise, what did I give you? I gave you two surfaces, right? The data is two surfaces, and to your eyes, those two surfaces look like a mullion profile, right? That's the key part of this, is before you can do anything useful, you have to look at it from that perspective. You can't just look at it and go, oh, it's a mullion. Because the computer goes, it's not. I don't know what a mullion is. I only know ones and zeros. I see two things that are called surfaces. By the way, if you were a guy who was good enough at computers, you could probably take those surface definitions and go all the way down to ones and zeros. We normally don't do that, right? Okay, so I have not actually given you E1 and E2, right? So those go away. So actually, that's part of the process now, is how do I go from that guy, bring him over here, and the first step is what I want after the step one. Let's erase this real quick. So step one is, at the end of it, we get out E1 and E2. That's got to be step one. Because unless we have E1 and E2, we don't just get to look at the thing, and we as engineers look at this thing and we go, well, of course, like the major axis is perpendicular to the longest side, right? The computer doesn't know that. The computer literally, again, I'm drawing it as a rectangle. The computer only knows, custom pen, erase. He actually sees, I'm going to exaggerate it here, that. Right? He sees that. He doesn't know anything else. So he just sees two pieces of geometry, right? So it's our responsibility to say, project onto that, what are these mathematically? How do we come up with those? Does that make sense? Once we have those, what do we need to do on step two, just broadly speaking? If we have E1 and E2, what can we do next? Ideas? One line? Say it? We can rotate it, right? Because to rotate something implies that you can have an angle for something, which means that you probably need to have two vectors or something. You can't just have an angle against nothing, right? Okay, so we're just going to call this next part, rotate. We don't even know, we don't have a name for this yet, just create some vectors, right? And then rotate based on those vectors, right? So then you end up with this, right? So what feeds into this guy? This guy obviously feeds in, and so will he. Everybody agree? That would be somewhat of a good start? Okay? So I'm going to save this, because that's, remember we talked about it, version 1 of our script. That's our first stab, that's our first iteration of creating some sort of, let's see here, smiley modules, advanced training, smiley face training, facades. So we need to update this now. So this works on paper. You say to someone, this is what you say to your drafter. Please take these surfaces, create these vectors, and by the way, these vectors have to look like this. And please rotate that original geometry based on those vectors. Is that specific enough to what we need to do here? Probably not. So let's go into version 2 here. Right? Let's get a bit more specific on what we actually need to do. So create vectors. This one's called create vectors. That's not good enough. The computer doesn't speak English. So what do we need to do? We need to come up with something mathematical that gets us that based on this. What can we do? Any ideas? If you had to say it in words, say it to me in words, which way E1 should go and which way E2 should go. Based on the picture on the left. If I was just a stupid guy who you needed to do the work for you, or else you're going to have to do it, but I'm a guy who's just willing to take instructions from you and do it all day long. Save you time. How would you describe it to me? Which way does E2 go?
Minus x plus y.
How do I create those E1 and E2? It has nothing to do with the global coordinate system, right? E1 and E2 is the local coordinate system of what you've been given, right? There's obviously a relation of those two coordinate systems, to each other. So if I go down here, the way I've drawn it right now, E1 and E2, there's a certain theta between them. But it also could be in 3 dimensions as well, right? We're projecting this in 2D. So the question is, just from first principles, if you were to sit here and you were to say to someone, where are those 2 vectors? You would sketch something that looks like this. But you're taking a lot for granted there. Why did you sketch that picture? What are the rules that are inherent in the picture I just sketched? Remember, it's all about rules. Okay, I drew 2 lines. Let's pretend it's 2 lines, right? Because geometry is a bit easier to say. Okay, 2 lines. We talked about this last time. Lines have 2 points, right? What's defining the endpoints of both of those lines? One at a time here. That might be the easier way to start. So this line right here that I'm showing is only one line. What determines his point A? And what determines his point B? Centroid, right? A would be the centroid of that shape. Why?
Because you want to rotate at that point.
Yeah, that's fine. That's the thing is, we have to put it down now because otherwise the computer doesn't know. So we know one of the rules is that we need to get the centroid. But we already have the centroid, which is good, right? So A is done. But how do we get B? That's where it becomes a bit difficult, right? Why is B not down here?
Along the local axis.
What's the local axis? What defines the local axis? Remember, I'm stupid. You can't just tell me local axis. As far as I'm concerned, if you told me draw 2 lines and they both start at point A, maybe I do this. Why can't I do that? What's wrong with that? It's in line actually with the way I've drawn it too. It's in line with these guys down here. That would be awesome, right? Then we wouldn't have any problems. So what's the rule on why I would do this initial sketch rather than the final one? Why is that one correct? A to B correct? You guys know it. Just say it. But there is no local axis. Remember, we're on version 2 here. In version 2, we have to consider only what we have. There is no local axis. All that exists at this point in the script right here, is 2 surfaces. There's no local axis, there's no mullion, there is nothing other than 2 surfaces. Everything that you think about outside of two surfaces is you thinking of that, and not the machine thinking of that. And that's the problem. You have to translate your thoughts into the machine. So that image I'm drawing there is actually just for reference only. All you have is this. So you did just say to me, we need a centroid. I told you, we have a centroid. We already spent the lunchtime session on the centroid, right? So now the question is, okay, great. How, based on now three things, because we do have a centroid, so that's kind of made his way into the picture here. What now, based on all three of those things, how are we going to take those three things and come out with a centroid, another point, let's call it, just for the sake of argument, and then as well, I'm going to keep it kind of consistent. Something like this, right? And I've drawn it incorrectly. So the new information that we want to come out with at the end of this is this one, which also gives us this, right? What defines that vector? It's a vector, really. We're talking about it like it's a line, but it's a vector. The centroid of the two surfaces, right? You're saying that?
Yep.
But even if we talked about this in the previous lessons, if I drew the centroids here right now, that would probably be there, that'd probably be there. The centroid I'm showing here is the centroid of both of them, which we discussed in like lesson 2. So this guy would obviously not give us, this guy over here.
Okay.
What's the rule? What's the main rule that comes into play when you look at something inherently? If I showed you this one, you right away would know where you'd want to draw those axes, right? If I showed you this one, you'd know right away that, right? If I showed you sort of that one, I'm just being an engineer right now. I just kind of know that's roughly speaking where we'd put it. We wouldn't put them like this, right? We wouldn't put them like this or something like this. So what's the rule there inherent in all of those? Yeah, you got the first part. It starts at the centroid. But the orientation of each one of these is now the big problem, right? So why am I drawing a line in this direction? What's the rule there? Parallel to the what? Yes, it's parallel to you're calling it perimeter. I would say the longest side. So this one is parallel to the shortest side, and this one is parallel to the longest side. Now that's a rule, right? You take it for granted because you're smart, but the computer is stupid, so he needs to be explained that the long side I need two vectors. One's parallel to the long, starting from the centroid, and one's parallel to the short. So in other words, before we get this picture right here, actually, we would need to get out, I'm just going to circle it kind of, this piece right here, right? So if we wanted that line, the first thing we'd need to do is pull out, let's say, that piece right there, and then that piece would actually kind of allow us to create something parallel. Does that make sense? Is that okay, guys? So we'll call this piece A. Here's piece A. Piece A will allow us to create vector B, right? It will easily, and then also this guy right here, right? Call him C. He'll be able to come over here. He comes over here, and then he helps us create D. That's it. That's the right answer. Well, the right answer for at least what we have, right? We need to find which direction of what we've been given is the long direction, and which way is the short. Okay, so that's all nice and good right there, but what do we do with that information now, right? Because obviously the next question is okay, we got the centroid. How do I do A and C? How do I grab that information out of there? How do I grab those vectors? There's an inherent vector in there, right? So let me save this again. All right, again, the question now is more of a, if I give you, so we have an intermediate step here that we have to expound upon. So if I give you this and this, again, that represents the two surfaces, how can I determine this guy and this guy? In fact, he's like this. What's a rule that allows us to take in any sort of two surfaces? Remember, they might look like this eventually. We don't know. And in this situation, it would probably be like this distance, and this distance, orthogonal to each other. Any ideas? So this is where you might need some help, right? Because you might sit there and say, I don't know. There's a bunch of different ways to do this, right? There really is. First things first, these are called what in Rhino? Surfaces, right? What are they called in Grasshopper? B-reps, right? And then other softwares, they're called other things, but we're using Grasshopper because we're Facade people and that tends to work better for us. So the first thing we can do is come into Grasshopper and kind of look for some tools that might help us. Just like we had in here, we knew this guy's going to be someone who's very important to us, right? Because we need some tool to help us do it. Maybe, since it's not so straightforward for us to actually come up with the idea here, we could come up with it from first principles, for instance, right? We could say, hey, listen, what I want to do is I want to find out all the points along this thing, and then I'll do some math to orient those points, you know, in a certain direction. I don't know. But it's not so straightforward how to deal with this, I think. So you can come into Surface, and you can start looking around for stuff that might be able to help you, right? So we talked about deconstruct, right? Deconstruct was the main word of if you want to take something apart and look inside of it. So if I take this geometry, which should be right here, and I deconstruct it, you see here, it gives me the faces, the edges, and the vertices. And that's why you see, when I click here, you don't see any of these like other pieces of information, because we've actually looked in the inside, right? So we could sit here now and say, can we play with, instead of playing with the geometry, can we play with the vertices to be able to get out effectively, you know, A and C here. A and C are the big things right now. You can't go any further with this until you figure out a way to make a rule that allows you to take these two surfaces and convert them into those two vectors, or those two lines, whatever you want to call them. We can't go any further until we figure that out. So whatever we have to do, whether it's playing with the objects, remember it's the hierarchy of things. We talked about this before as well, I think, that just like we said, there's a line. Whoa, 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 can't have that. Remember before we had said there's lines that have points. Points have coordinates, right? So this B-rep, he has a bunch of stuff inside of him. He has edges, which have endpoints, which have coordinates, right? So those pieces of information could be very useful to us, because there is no apparent, no one's sitting here right now and jumping out of their seat and going, oh, I got it, right? So it's either the information is inside of this objects, or we have to create some new information based on those objects that will help us. Anybody have any ideas of what we can do to come up with C and A, provided this, 1 and 2 here? This is what's going to make you a good computational engineer, if you can start to... This is the problem. This is one of the things you'll need to be able to do is think of unique solutions for unique problems. This is it right here. And you're an engineer already, so you should be good at that. So what I've given you a B rep. And inside of that, there's edges, there's endpoints to those edges. They call them vertices sometimes. How can we finagle this stuff on the screen right now to come up with effectively this? It's there, right? We see it on the screen. In the green, there's part of the green that is this black line I just drew. If I put it right over top, right, you can hardly tell the difference. I can see it. So the question is from here down to here, that would be one of the vectors that we'd want, right? In the same way, if I drew the other one, it would be from here to here. No one's arguing with me on that, right? Engineering-wise, I got it. I'm not a facades engineer, but I understand enough about it to do it. So how are we going to do it, guys? There's got to be a way. So we could use those points potentially, right? But are there enough points there? Are there too many points there? One would say. Too many, right? Because obviously these guys, they're not eligible candidates, right? This guy's kind of an eligible candidate, but actually not perfect. And what are we supposed to do? Grab this guy and then this guy and have a crooked line? No. So here's where you might want to come and either Google searching is going to be difficult, but you come and you tap a guy like me on the shoulder and says, what do you want to do? I think if it were me, I'd do something called a bounding box. Because what I really know you want is you just want a box. So if I were just a guy who came out here and did, it's going to be hard to do because it's on a slant, but I want to basically draw a box, roughly speaking, around that shape that you guys have here. I didn't draw it quite right, but effectively that's what I'd want, right? And then I'd take the shortest side, I'd take the longest side, that would be it, right? Well, there is a feature in here, it's called bounding box, which takes in a set of geometry on a certain plane for the operation, and it creates a bounding box, right? But I'm learning here again that the bounding box seems to be oriented. So look, he's created, let's see, this is per object now. So see how I right click it and it becomes two boxes? If I do union, it's both. So recall, this function is a function that returns the minimally sized box, right? That goes around all the geometry you've created for it, right? So it's a good candidate for what we need, right? What's the problem here? Again, if I do union versus not union, you can see it again. It's just doing it twice now because it's not doing it for everything. Problem here is if I rotate this again, you'll see. See how he's coming along with the ride with me? He's still oriented. This box, no matter what he does, he's not oriented the way we want. And that comes in here. He goes, bounding box, orientation plane. So even he's not going to help us because he doesn't give us an orientation, right? He just gives us a box, period. But that box is oriented, again, this is the minimal size box that will encapsulate that geometry that you gave it. So if I zoom in here, let's get clever here. It says it's orienting this bounding box to the XY plane. Well, and that's what it's obviously doing because it's parallel to the XY plane. But what happens if we were to, I don't know, and again, I'm making this up as I go here. Ooh, now we're starting to get something, but it's still not looking right. So it's not going to work that way. So the key here is that's not going to bail us out because he doesn't actually give us, the orientation. So no thank you, we can't have you. So he's got to go. So we tried that, we failed on that one. Remember, we also have midpoint, where's the centroid? Oh, that is the mid. Yeah, midpoint. So that is the centroid. So remember, we also have this information here. Because this is where we're inserting it, right? We're going to do this math before we get to all of this stuff, right? So eventually, we'll have geometry from this algorithm we're developing here going into here. Okay, so we want a line that would emanate from here and kind of go up this way. If I just look here at the edges of what you've been given, again, hiding some of the original input, what could we do just based on the edges that could help us? There it is, the longest size. Guys, whenever you see how up here it says 0, 0, 0, 1? At this stage, everything I give to you, just assume for right now, the answer to that is flatten. Okay, whenever you see this dotted line, when you're first getting started off, you can get rid of it by saying flatten, and then everything's going to be okay. All right? Now, you say, hey, it's about length, so let's get the length. And we said before, if we do panel, there's a lot of numbers. They don't mean anything to us anymore because we don't know which one is which over here. So what are we going to do now to make sure that we use these numbers correctly? Sort. And if you did your smiley face training, you'd know that we are officially in the realm of Chapter 2. Because we're using a metric right here to sort the original data so that now, if I go and I say list item 1, it's either the shortest or the longest. In this case, I think it's the shortest. Yeah, he's the shortest. So we've actually, if we reverse this list by right-clicking and say reverse, we'll get the longest. So we're getting there because your rule is correct. We know that the longest side hopefully has the longest line, but we're wishful thinking here. That is the longest line, but it's not the line that we want. We're getting closer because that's obviously one of them. What could we do here to help hedge our bets? What's the problem here? Yeah, so we just can go explode. So let's explode, but let's do the explosion kind of back here. And you see how the picture changes now between the two of these, right? Right, so now the data, we're just processing data here. We're just kind of cleaning it up, getting it ready for, for what's coming next. What do we do when we see this dotted line? Flat. Oh, hey, how you doing now? Right? Everybody see that? Yeah, if I just get the endpoints of that. That looks right for the first vector, right? So congratulations. If I go vector 2 points, we're going to call that one E2. Congratulations, we have officially found E2 by a very simple algorithm, which is, please go in there and find me the longest line after I explode, right? And then I'll find that longest line, and that guy should be the guy who gets me to the top, right?
But it's not really actually the longest line because there's a corner like fillet on it.
He's a bit off,
Yeah.
right? But the vector is not about the length, right? It's about its orientation. Is his orientation correct? You're right. We could have picked, these 2 points, basically. As long as they're on that same orientation, it'll be okay. Question will be is, will that always hold true? That's going to be the question here soon. But for now, let's say it works. Because it asks a different question now. So is it the converse now that the shortest line is the other vector? Is that correct? No. Not necessarily, right? We just saw there's a lot of small little junk vectors down here. This might be the shortest one too. So we might get the exact same vector out for all we know. So what could we do now that we know E2, going back to paper here, if we knew E2, How could we get E1? You could rotate it 90 degrees, assuming what? Can I rotate it 90 degrees? All the time, Jane? What if I was a guy who gave you that? If I look at it top now, you'll see. He's in 3D space, right? So then it wouldn't work. Let's assume for the minute, though, that everything we get is in the XY plane. It might not be oriented correctly, but it must be in the XY plane. It's a pretty fair assumption a lot of times, too, I believe. So we don't need something that's completely generic. But just keep that in mind, that this will not, you need to understand the limitations of your script. So if you have something now that's out in 3D space, and which could happen, you got something like a Morpheus Tower, where there's a member out here, like this, then this will not work, right? But you're right, so we could rotate that vector 90 degrees in the plane. So what do? We say rotate, little emojis come up, it says rotate a vector around an axis, rotate an object in a plane, that sounds about good. It's asked for a piece of geometry, it asks for an angle in radians, I'm going to change it to degrees because we're those kind of people, and the plane is XY. Again, that's hard-coded in there. You change the geometry from out of XY, all of this is going to be invalid. A is now going to be 90 degrees. And I can't see it because it's not the vector's not visible right away. But we can display vectors, called vector display, to make very pretty pictures. So we can, all it wants is an anchor point and a vector. We have a vector here. And now if I pick the anchor point, which should be what? This guy. And you see the arrow just came up on the screen, right? And if I grab this guy, is that acceptable for now? It's not exactly the picture we drew because we're not completely in control of which way it decides to draw it. It drew it the opposite way. But is it good enough for government work? Does it really matter for IXX whether the axis goes left or right? Is the number positive or negative mattering? Probably not, right? Doesn't matter too much. So I would say at this point we have E1 and E2. And we had said that was what we were out to get at the very beginning of all this today. That was one of the biggest things. So we are now solidly here. Okay? Next step was the rotate using those two things, right? Which we might not even, you'll see soon, we might not even need both E1 and E2 for that. So that's where we're at the end of today. You've gone through the process again of, in one small little step of these 3 steps, you've seen now multiple times, each one of these steps, this is why you have to start zoomed out. What's the problem? What's the big problem? I need to find a centroid, rotate the GCS, and then do some sort of integration. If you don't break it down like that, you can see inside of each one of these is a bunch of other types of little things you have to do. And if you don't break the problem down very specifically, you'll never get anywhere at all. And you've seen now, 5 hours in, we're still doing this. So it's really important to now go back, try this method to do exactly what I've just done here, to go from this geometry to effectively these 2 vectors. Because we now know, unless we can do that, we can't do this problem. Also, I would, if I'm you guys, I don't know how many people did it for this one, we didn't really talk about it, but this idea of cleaning up your parallel axis theorem and duplicating it, whether you cluster it or not, is up to you. Obviously, that's going to be nice. We want our script to look nice and neat. All right? Any questions before we break for the day?
Can you share the script?
I can share the script after everybody's had a go at it. How about that? I've shared.
We tried it, but we got some problems. Yeah. Can you actually check? I tried to figure out, and then
Share it with me right now. Is it, or is it? Did you send it to me already? It's not the glass one, right? It's the one you were working on at work yesterday, right?
It's
Yeah. Shoot it to me on Skype.
Yeah.
We can look at it right now, real quick.
okay.
Skype it up.
Okay, you can just actually find it from the non-project.
Where is it?
Non-project and it's for binary.
Which one?
Lesson 4 concept.
Let's look. Same inputs.
Yeah, same.
My guess is it's going to break it. Step 1, 5 centroids. Step 2, draw the line. Step 3, find that centroid point. Boom. Okay, so oops. You're there. Step 4, step distance in the Y. So what are you doing here? So you're saying, here's my centroid, and we'd said before that the start point of this guy is actually the centroid of this first piece, right? There should be 2 pieces coming in here, though. That's your problem. Right? Because you need 2 pieces to do that with. Let's see here. Here's my centroids. Yep, there it is. Here's my, so your line is being drawn sort of in the wrong place too. So I'd say your line needs to be let's see here. X comes from these 2 points. So X has to come from there, and Y maybe comes from here. Nope. That's not it. What am I doing wrong? We construct a point. Oh, sorry. So I want the line that's kind of different to what you just drew. So it's definitely, this guy's one of them, except for he needs to also be deconstructed, and we have to just create a point that starts at his X and ends at his Y. Oops. Again, it's kind of just reverse engineering. So I want this line to end at his Y location and his X. There we go. Where's the second point? Oh, there it is. Just can't see it. And these 2 points here, they should just be these 2 points here. You see that? All I'm doing is massaging around. You had neglected that the parallel axis theorem is actually taking in. We need multiple ones of these lengths because we're summing up all of these, right? So you have to use the 2 centroids. So we have 1 global centroid and 2 local centroids. And then it was just an issue of the axis, like the picture that you're drawing is incorrect. It's not orthogonal to the axis for which we want the moment of inertia. Does that make sense? So that's one of the things. I'll save that for you. I'm sure you're doing the same problem down here, right? So you can just duplicate that. And then you would be 1 step closer to where you need to be. And again, we could do the quick area moments. 2.472 IX area moments about world coordinate systems about centroid axes. 3.001. So we'd have to look into what's going on there. But remember yesterday we had said there was a lot of things that probably could be going wrong here. I think we had talked about that last lesson, where the mathematics of it might be off. You want to get the IXX here, which means you need to be taking the moment of inertia about the x, so that was definitely wrong. We're still not matching. Squared.
Yes,
Let's just double check. So this is our,
y direction or is it x direction?
well, it says this is the distance of those centroids to the x-axis, right? So that would be the correct r as long as it's being shown correctly. Ah, wait a minute. What about this? I don't think it's x over 2 anymore. 3.007. You see that? Did everybody see that? Yeah, 3. Yeah, there you go. So the math was off, as you said. Like, you didn't need to play with this anymore, this math here, because if you make this correct, then everything else falls in line. So I'll save that so then you can actually incorporate that down here. How long did that take you, by the way, to do all this? Yeah. An hour, yeah. Guys, that's all it takes, is an hour of playing around. And then at least you come into this and you kind of know, I think my issue is this. I don't think my issue is Grasshopper. My issue is math.
Yes.
It's just, and in your case, it was lists. Your issue was more or less, I don't know how to play with lists yet. Because you guys pay attention to like the wires. See how this one's solid? And this one is kind of like see-through. And then this one, if I do this, he's kind of dotted. Like that. They matter, because what that's telling you is, if you see a solid line, it means you're pushing around one item. If you see a see-through line, it means you're pushing around a list of items. If you see this one, and this one's more advanced, this one means you're pushing around a list of lists. It matters, because when you design as a computational engineer, you're designing with data, and the structure of that data is everything. So in this situation, the computer's actually doing something for you. When you have 2 x's and 1 y, it's making a decision for you to make you 2 points, right? We can't really see the 1 right now because it's hidden if I hide this, right? And you should have known, if you were grounded in your first principles, that actually the parallel axis theorem should be taking each one of these surfaces and doing a calculation on it, in which case I need 2 r's. In which case I need to see 2 lines. So that's really why it's important, just getting on my soapbox again about the first principles. If you don't have that, you'll never figure this out. So you had a data problem, but also you had a little bit of a math problem. But at least you knew that you were close. All right? So I'm not going to do the second one for you. You can massage the second one. And then you can take today's. I'll let you guys have a couple days to try, and then I'll post the script for today's lesson later. And I'll post the video today as well. Okay, thanks for coming.